And thanks a lot for the invitation. It's really a pleasure being here. I'm very excited. So I will talk today about novel anomaly detection techniques to accelerate new physics discoveries at the Large Hadron Collider. Yeah. Okay, so let me set a little bit the stage. The beginning of this century marked a big expansion of our knowledge of the universe from the very small to the very large scale. Among the most remarkable discoveries, there are the discovery of the Higgs boson at the LHC, which completed a great theory of science, a standard model of particle physics, and the measurement of gravitational waves by LIGO and Virgo collaborations, which proved general relativity. However, there are still a lot of questions that we do not have answers for. For example, the standard model particle physics doesn't account for neutrino masses. Gravity is not included in the theory. It only explains 5% of the universe. In fact, there is no standard model candidate for dark matter, and also doesn't explain why there is anything at all, because it cannot account for the baryon-antibaryon asymmetry. So probing the fundamental structure of nature requires complex experimental devices, large infrastructures, and big collaborations. So we want to answer to these fundamental questions. And while scaling up the experimental systems, also data scale up, and now we're collecting vast amounts of data, which we need to analyze. So in this era of science, machine learning can greatly accelerate time to discovery, allowing us to test hypotheses significantly faster, enhance and automate performance and operation of detectors and accelerators, and eventually also save and maximize potentially lost data. So I'm mostly working on the Large Hadron Collider, so where we have the biggest challenges in terms of big data. So I will focus on this, but I'm also involved in machine learning for liquid argon TPCs, which are the main let's say, building block of the Dune experiment. So the LHC is a ring of 27 kilometers located at CERN in Switzerland, or part in Switzerland, part in France. And it collides proton beams at a huge frequency of 40 megahertz. So the collisions happen at 4 interaction points along the ring. And each collision produces thousands of particles. So we place huge detectors around the collision points, indeed, to identify all of these particles. And these detectors are very high resolution. They have like 1 billion of readout channels used to detect, indeed, the particles coming out of the collision. So we're dealing with extreme data rates of petabyte per second. At the same time, collisions which produce interesting products, so for example, an Higgs boson, are typically very rare. So here it's basically the probability that the process can, say, be produced for many different processes. And for example, the probability of producing a Higgs boson is like 5 to 9 orders of magnitude smaller than producing only jets, which is something that we call background, that we care less about. So when you search for new physics, you're looking for something that is even more rare than the rarest standard model processes. So this is a big challenge. And how do we do searches for this type of new physics at the LHC, or actually what we don't do? So research under the scientific method starts from observation of the real world. But at the LHC, what we do instead is to start from a theory, which in the pre-Higgs era was mostly standard model. And then in the post-Higgs era, it's still a standard model to observe some rare processes, but even more rare new BSM signals. So in some sense, we no longer learn from observations, and we, in fact, we perform blind analysis as the only way to perform these searches. So this, say, workflow works very well when we know what to search for example, an Higgs boson. And in this case, we put a strong inductive bias to guide, let's say, each step of the data analysis workflow. From data processing, which is basically going from detector raw data to physics objects, to data reduction, so computing resource. So, I mean, it guides also the choice of computing resources up to the final high-level features analysis and statistical interpretation. So here, like, are two, say, distributions which show like an Higgs boson like decaying in 2 photons and above a smoothly falling background, or here an Higgs boson decaying to 4 leptons. So it worked well. However, now in the post-Higgs era, we are looking for new physics, and we have like a huge amount of theoretical models. And for example, these are like summary plots from Atlas and CMS, which are, are unreadable, but just to let you know that each of these lines is like a search that you are performing. So it's a theoretical model. And then what we do is that, for example, there is a new particle predicted, and so we set some limits on what the mass of this new particle could be. So in fact, for each of these, the theoretical model, we perform and design an analysis which aims at isolating the specific signal, and that's how we manage then to set the limits. However, with thousands of these analyses, we have not found any significant evidence for new physics. So we start thinking if nature perhaps is different from all of these, and we started asking if we're looking for the right events. In fact, any data processing step could be a signal killer, or is the right event even there? Because event filtering, in fact, starts very early in the data processing. So the community started thinking on how can we generalize, and rather than starting from a signal hypothesis, we could go back looking at data. And if we identify an anomalous signal, then we could formulate an hypothesis. So there have been many new ideas recently that make use of deep learning to learn directly from data how the standard model looks like. So basically eliminating the signal priors and search for anything anomalous with respect to the standard model. And this is what we call anomaly detection. So we want to design our anomaly detection analysis, and we will start with the, let's say, final states that we know pretty well, and these are dye-jet resonances. So first, jets are spray of hadrons initiated by a fundamental particle of some kind, which can be gluon, light quark, or W or Z or Higgs bosons or top quarks. And these are clustered into one object with some jet clustering algorithm. And then these jets have different properties depending on the mother particle. So characterizing these jets is a key task at the LHC, because if we can classify which particle it comes from, these allow us to expand the new physics searches or standard model measurements, and also like measurements that say more related to the Higgs boson. So here is an example of new physics scenario in which you have a graviton or a radium being produced, which decays to like a vector boson, standard model vector bosons, and then to quarks, which then become jets. So different characteristics means a different particle and physics processes. So it's a very important task. And exploiting such characteristics allows us in particular to suppress the abundant contamination from background jets, which come from light quarks and gluons. So for example, you can see here in this cartoon that the background jet looks very different from signal jets, where you start having like instead these 2-prongs or 3-prong structures or even more. So these let's say characteristics is basically identified or characterized by what we call jet substructure observables. Or one can also exploit the flavor content. So for example, heavier quarks like bottom quarks, they basically decay close afar from the interaction point, and so they give some displacement, which can be, it's an information that can be used. So for here are some example indeed of jet substructure observables as to understand like how what discrimination between indeed the signals and background. So this is the jet mass, and this is another variable that tells you like how many prongs there are in the, so how many substructure there are in the jet. In fact, background, it's very localized here with signals instead here. So what do we do when we want to make an analysis? We want to make a search in which there is a new particle, A, for example, decay into 2 particles, B and C, which then decay to jets. So we have 2 jets, so that's what we call a dye-jet resonance. So what we start first looking if there are 2 jets in the collision event, then we look if the 2 jets are consistent with some standard model particle, and if yes, we reconstruct the invariant mass. which is like this distribution. And then we look if that is consistent with the new resonance. In fact, like this is for the background is smoothly falling, and if the two jets are coming from a resonance, then you expect like a bump. So the usual assumption, like we do it usually, it's that A is some unknown new particle, and B and C are instead some standard model particles, such that this characterization is, let's say, supervised. So digit resonances have been studied extensively at colliders with many different hypotheses on how the jets look like. And but there can be many more beyond standard model scenarios not covered by dedicated searches, or there could be let's say a BSM signal that we never thought of. So it's a natural place to explore novel analysis strategies. So now, instead of putting an assumption on and perform like a supervised classification for these jets, so we want to tag them as anomalous with no assumption on how it looks like. So do it fully unsupervised. In this way, we train directly on data, and we do not have to rely on imperfect standard model background simulation. So the anomaly detection search starts with some preselected data, then you train a model which define also an anomaly metric, then you apply selection, and then from these events that are surviving this selection, which are the most anomalous, you perform this bump hunt looking for the resonance. So here is where there is a lot of machine learning ongoing, of course. And it's not, I mean, there are different ways in which we can, let's say, design a method for training only on data and perform in a supervised, let's say, supervised classification. We tested, I mean, there are many literatures, and we tested a few. In particular, one can first, so let's say the most model-independent way of doing this is through autoencoders, where you learn to understand regular jets and then look for outliers. I guess you are all familiar with autoencoders here, but just to recap, you want to train on non-anomalous examples, which are our, say, background-like data, and then learn to reconstruct them. And then by forcing the information through a bottleneck, you focus on core features of these normal samples, such that then when you test the autoencoder on unknown samples, it fails at reconstructing exotic examples, giving a high reconstruction loss. So this is the most model-independent way, most supervised way of training anomaly detectors, because we're not putting basically an assumption on the signal. There are also other ways which, let's say, have some assumptions. In this case, in, let's say, weakly supervised fashion, we try to separate instead the two groups of jets in order to learn to identify signals. So in a supervised, pre-supervised strategy, typically you train on pure Monte Carlo signal, pure simulation signal and background, and then you give labels. But if you don't have, if you are training on data, then you do not have labels. So well, you need to think about something different. So you can instead create the two mixed samples of signal and background events with different purities, and then train a classifier on these two samples to learn to distinguish indeed signal versus background. Now, the higher is the signal fraction here, the better is the classifier performance. Then model dependence here comes from the assumption of different purities. So you need to put some assumption in creating these two mixed samples. So we use the fact that we expect indeed a bump, so a very localized excess of events over the top of the background. So in particular, this means assuming that the signal X is a narrow resonance with a certain mass. So with this assumption, your signal-rich sample will be like indeed this narrow window around the expected resonance mass, and your background-rich sample will be the data outside it. And then once you put this assumption, you create these two mixed samples, then you can train the classifier on to distinguish between signal and background, and then define an event anomaly score. Now, of course, you need to scan the full spectrum because you might have different masses of the resonance. You don't know where the resonance lives. There are also other methods that we investigated to do this weekly supervised training. They all assume an error resonance. So in this one, tag and train, we reach the purity from anomalies before the training by using an autoencoder. And in cathode, instead, we use normalizing flows to estimate basically the background distribution. Then we interpolate in the signal region and then sample. There's still one more method, which is quasi-anomalous knowledge, which has been introduced by Phil's group, where the main idea, so it's a kind of an hybrid approach between model independent and standard searches, because the main idea is that you can encode a prior knowledge of how a signal could look. And then you train a density estimator, they use normalizing flow, on mixture of simulated signals. And then also an additional one on background simulation. So in this way, basically, you can create these D space of the background loss or multiple D, not 2D, depends like how many signals you have. You can have multiple dimensions. But okay, let's say you have just one signal. So you have the signal loss and the background loss, and then you can select events with high background score and low signal score. So because you expect that a new signal similar to the ones that are encoded are useful. So this can also be made more signal specific if you if you use only, let's say, the signal that you want to probe. So this is more like a supervised search. Okay, so we have some new CMS results using all these approaches that was just published. And since we probed like a lot of methods, all with different challenges, there were many people involved, and there was also a major contribution from the CMS MIT group. So we are many different institutes, and there was also like a nice physics briefing on the CMS news if you want to check it. Okay, so we said that the different methods, they have, let's say, different level of model dependence, but also they all use very different kind of different inputs. So with the variation autoencoder, which is, let's say, the most model independent one, we really only use the 4-vector of the particles and no other informations. While instead the other ones, they use more so high-level features, which are basically related to the jet substructure, so they're very sensitive to it. While instead with the autoencoder, we basically let the model to learn or extrapolate these kind of high-level features. So how do we test the performance? How do we compare the performance? We basically decided on a set of signals. So in a way that we could scan all the different topologies of the two jets. So these, so there can be, let's say, so basically we're trying to cover as much phase space as possible to see if really these methods generalize to many different models. While typically what we would do is an anomaly, it's a supervised search for each of those, which anyways we are not able to do in CMS or in Atlas because it's just too many combinations of possible signals. Okay, so we can prove, so the first way to test the performance is that we can inject a signal of in the background simulation and then calculate the sensitivity of the methods to it. And we can do it by also changing the amount of this signal, so how many signal events there are. And this is basically changing the cross-section. And if you look, so these are indeed, let's say, the discovery sensitivity as a function of, let's say, of how much signal there is. And we compare the methods also with an inclusive search. So basically a search in which we don't do anything. And we see, for example, that all the anomaly detection methods improve the sensitivity with respect to an inclusive search, which is a standard way of doing analysis in CMS, by a lot. So this is really nice. We see, though, that instead, the variational autoencoder is the one that has, let's say, less power, is actually indeed fully model independent. And eventually, I think that a more expressive neural network architecture and maybe more inputs would yield a better performance. So the same is shown also for another type of signal. So before it was like a simpler signal. This is a more complex signal, and we can see that again that we see a lot of improvement in discovery sensitivity, and so also means also we find that some models that are also, like I say, the relative improvement of the models change. So it's like basically saying that not every model is sensitive in the same way to the same signals. So, for example, the variational autoencoder is way more sensitive here than for the other. So we also perform a bump hunt, of course, after all this work. That's what we're doing. We're looking for a resonance, indeed, but unfortunately, we don't see anything. Since we don't see anything, we also try to understand basically like if there would be something what would be, let's say, the cross-section of the process to say, oh, I have an evidence or I have a discovery. And also in this case, we see that basically an anomaly detector is way more sensitive to a very rare signal with respect to other standard approaches. Okay, so this brings me to my next section, in which I wanted to discuss a little bit the fact that I was saying at the beginning that we're dealing with a huge amount of data, of terabit per second. And because of that, we have in place a system of multiple levels of filtering. We start with, say, with terabyte per second data flowing out of the detector, and then we filter them first with a hardware trigger. So where this is like all on field programmable gate arrays, so it's all FPGAs. And this stage already rejects 99.75% of the events, and bringing down the rates to 100 kilohertz. So at this point, we have another level of filter where other 99% of events are rejected, and this is all since the rate is very low. Here or it's very low, it's actually quite high, but lower. We can actually have everything implemented on CPUs and GPUs. And then finally, so we end up with 1 kilohertz or 1 megabyte per event, which we store and analyze offline. So with 40 million collisions per second and 1,000 store, we might just be writing the wrong events. In fact, the trigger algorithms, so the selection algorithms that are here in the level 1, the hardware trigger, or also in the, let's say, CPU trigger, are quite model dependent. So they are made to isolate phase space that we think, where we think physics, the most interesting physics is. So any other signature that we did not think about could have easily be discarded. So that's why we started thinking on how to correct this problem as early as possible in the data reduction workflow, in particular in the hardware trigger. How the hardware trigger looks like. So the hardware trigger reconstructs all the particles in the events, but in a very, let's say, coarse way. So it's way, because it has to be very fast. Here, like, for example, we have like 4.2 microseconds to reconstruct muons and jets and the missing transverse energy and the taus and electrons and photons. And because of that, we don't have time to do like a full reconstruction of the detector like we do offline. So we have some objects which then we use to define filtering strategies. So we have like hundreds of algorithms, typically looking, for example, for one jet with a certain transverse momentum, or in central in the detector, or you can ask also like some muons, or a single muon or two muons with a certain PT and characteristics. So in particular, we would like to indeed deploy anomaly detection here, taking advantage of all the objects that are reconstructed. But while this system is now, let's say, it's working very well, but it is giving like a very coarse reconstruction. For the high luminosity LHC, we'll have a way more performant trigger because we will be able to also reconstruct the tracks in the inner part of the detector, and so we can actually do the combination with the calorimeter and make it like a way more high resolution reconstruction. And this will give us a lot of advantages for anomaly detection because indeed of the higher resolution of the inputs, which also means that we have to scale the models. Fact about scaling the neural networks, obviously deep learning algorithms can become relatively large and so exploding in memory number of operations. And that's something that we cannot afford in the trigger because, as I said, like we have, for example, now 4.2 microseconds to do everything. So you cannot put like a very large neural network. You have these strict latency constraints. So even for phase 2, we're still in the microsecond range, though it's a bit, it's 3 times. So now we have 4 microseconds. At high luminosity LHC, we'll have like 12 microseconds, which is a huge increase, but still it's a big challenge. And also we have scarce resources because we need also to build all the objects that we're going to use as input to a neural network. So we don't have a lot of space for a network. So the networks need to be very fast and tiny. And this is particularly challenging. So we build our own tool to achieve that. This is called HLS4ML. You probably maybe heard about it. It's a package for automatic translation of trained neural network into a firmware project. You start with your favorite model in Keras or PyTorch, and then the tool converts into a firmware project using high-level synthesis, which is a language which is like C or C++. The cool thing here is that there is a lot of optimization in the tool for efficient inference, so to achieve really low latency and low resources, and this is like what we need for indeed our trigger application. It's very customizable with tunable precision and parallelization, and also it now supports many architectures, and then you can also use an interface to the library, and has also profiling utilities and so on, and debugging. So this is not enough. So actually, internally, HLS4ML exploits many different techniques that happen more at training time. In fact, you need to do some tricks during the training in order to achieve an efficient neural network. So things that we say that the practices that we follow usually are compression or pruning, where you can train by removing iteratively some of the connections that play a little role for the final decision. So basically, this is zeroing some of the multiplications. And also, we perform quantization-aware training. In particular, we find that neural networks are more efficient if we reduce the precision, so from a floating point to instead like a few bits. And this, you can do it actually with some tools like QKeras, to embed the number of bits, the precision that you want in the training, and then keep the performances very high. And then also internally, you can exploit the fact that the FPGAs that we're using in the trigger can have a high degree of parallelization, so you can tune how much you parallelize, and then get maybe higher latency or less resources, and so on. Okay, so now we want to put an autoencoder in our trigger. So because, as I said, like the anomaly could be discarded, we only have model-dependent algorithms, although they're kind of loose. And so we think that there could be advantage in deploying anomaly detection at the trigger level. So we developed a tiny autoencoder, which use level 1, so these trigger objects as inputs, and the inputs are chosen in a way that we can represent the full collision. So not only jets in this case, but really like the full events. In fact, we input the information about muons, electrons and photons, jets, and also missing transverse energy. So everything that is reconstructed in the trigger. We use a variational autoencoder, which is trained on unbiased data collected by CMS last year. So this is about like 10 million events. And we train it in a way that it can learn to reconstruct the average collision event when no filtering is applied. So that's what I'm saying with as unbiased data. It's really like a data set where it was not filtered, basically. So it's not that big. So we have only maybe like tens of millions of events, but it's very useful for this. So this average collision event typically looks like soft hadronic collisions with a large number of low energy jets. So that's what we try to reconstruct. And this type of background, let's say, is usually rejected by the model-dependent filtering algorithms. But now we want to still filter out this background by using the anomaly detector. So from a variational autoencoder, though, we perform a trick. We define the anomaly metric in the latent space. So we use the mu particular, and we square it. We found that to work pretty well and as good as using the KL loss or the KL loss plus the reconstruction loss, or some combinations of those. And why we do this? Because like this, we only need to deploy the encoder, and we can basically cut the model enough and also the latency enough. We use like fully connected neural network, and we perform quantization aware training with QKRAS to reduce the resources used on the chip, and then HLS4ML to translate the neural network into firmware. And then we need to finally integrate this firmware into the rest of the system. So by these tricks, we managed to have an autoencoder like which runs in 50 nanoseconds, and also use very little amount of resources on the chip, so almost zeros. Okay, this is the distribution of the score. You can see like different dashed vertical lines, which are different thresholds, which can be defined based on the trigger rates that you want. So you can decide like 1 kilohertz, you can apply a threshold that gives you 1 kilohertz output rate, or 10 hertz, things like that. And then what we did is like we decided on these thresholds, and then we checked indeed the rates of the events passing these thresholds versus time during the collisions. This was done last year, not on the production system, but on a hardware system, which is a replica of the production system, which allows us just to monitor. So we didn't take data yet. We just monitored what would happen if we would take data. And the rates are very stable. So we were very happy to see this. So this is actually a picture also of the CMS cavern where the whole trigger system is placed. So it's like a lot of crates and FPGAs. So this means basically that because one of the, let's say, of the things that people usually ask me is like, what if your rate explodes because the detector has some problems and so on? You don't, because typically in real time, you don't know things can happen, okay, in the experiment. Then usually if there are experimental problems, then offline, we actually filter out those events. But in real time, we basically don't do it. So it was nice instead to see that we don't have, let's say, sensitivity to any of these type of experimental effects. So then finally, this is like the most anomalous event in 2023 data, which would eventually be triggered by our anomaly detection trigger, which, by the way, we called it Accelerator. And it would be triggered by this and not by the other triggers. So it's really exclusive. It has a large number of jets, 12, and 1 muon. So it's very busy and unusual event. It's hard to say if it is compatible with new physics without, let's say, a full year of data taking and the full statistical analysis. So we'll see by the end of this year once we actually do that. Yeah.
It was triggered by the neural network. Do you have multiple different ones running in parallel, and it just that was the only one that caught it?
No, this is just the most anomalous, so the one with the highest loss.
Yeah, that's what I'm asking.
No, the traditional triggers didn't get it.
Okay, so it was recorded because of this neural network trigger.
No, it's actually
I'm missing if traditional triggers didn't catch it, then why was it recorded? I'm just missing something basic.
Because because the data set that we use for training and testing is an unfiltered data set, so it's unbiased, doesn't have. So from time to time we take some events without applying any filter.
Thank you. That was the key I missed.
So we will start taking these kind of events like now, basically, because now we just restarted the collisions and we're testing again, and we're going to put it online. So I wanted to mention that deploying the neural network trigger requires a lot of steps. Actually, we started this, I think, 3 years ago, and training the autoencoder and getting some performance was like 5 minutes compared to all the rest that they had to do, like a lot of technical let's say steps, and by including also the experimental. So you need also to simulate these in the experimental software and then check that the software matches exactly with the firmware. So I'm not going through all this, but it was a lot of work. So something that now we're working on is to automatize this workflow in order to have a quasi-online retraining, validation, and deployment. And I think that this is crucial to maximize the system performance. So this is some work that Phil's group has started doing. So this brings me to my conclusions. I just wanted to mention the challenges that we have in anomaly detection, which both online, let's say, and offline. So we have problems with robustness. In fact, spurious correlations enhances detection of fake anomalies. This is an example for the jet mass. Once you start applying, let's say, a selection on the anomaly, that on the anomaly score, you start having these kind of effects, which are typically unwanted, because this is like pure background, and it's pure background, and you don't want this to be anomalous differently from the other, let's say, parts of the spectrum. So in high-energy physics, we implemented methods that require a lot of data engineering, let's say, depending on the specific method. This can be reshuffling, normalizing, reweighting, or sometimes like brute force or adversarial training. We see that typically these methods affect the performance. So it would be nicer to have a more generalizable way of obtaining this type of robustness, eventually focusing on representational learning methods to embed the physics properties that we care about, rather than these spurious effects. Then we also, I think we need to think how we can exploit both simulation and data. I had a lot of discussion about this with Jesse and Phil yesterday. In fact, we can take advantage of the fact that data is huge in size, and also has the advantage of eliminating the need for calibrations. However, at the same time, simulation gives us the physics bias we need, but it is expensive. So how is there like a way to combine both? Then one question, one open question since a while, or long-hanging fruit, is how to interpret anomalies and make hypothesis tests. So do we just need the hint and then we build a supervised search, or can we do more like an hypothesis test without an hypothesis in some sense? Then it seems like from the CMS results that there is no anomaly detection method that is good for everything. So we might risk to just have a proliferation as we have for supervised searches, or for supervised searches. And maybe we want to ask if we can build a universal anomaly detector or combine maybe different ones in a proper way. And then I think for the trigger, also adaptation to varying condition is particularly critical, especially for anomaly detection, which is trained really on data, but also like for other types, because like you train on a bulk of the distribution, but that like the things change, like the beam, the proton beam, and also the detector changes even like, you know, very quickly. So we started thinking on ways like continual learning ways to have a system that adapts itself. So this brings me to my conclusions. Just wanted to advertise the next generation triggers project at CERN. which we need to thank the ex-Google CEO, Eric Schmidt, for donating to CERN 50 million to develop advanced data acquisition trigger systems for Atlas and CMS. And you can have a look at the CERN news here. And we're going to do like a lot of, say, fun stuff for fast machine learning, so fast reconstruction with ML, anomaly detection, efficient LLMs, foundation models, and so on. So we are hiring. Here I put like 2 of the positions we have now open as a CERN fellows, which are more, let's say, focused on the things that I've discussed so far for the trigger. But there are also more positions which instead are more on the machine learning side. So basically allowing us. So this is more about developing the tools that we actually need to port our physics algorithms to our systems. So if you want to hear more, you can just write me. And that's it. Thanks.
Thanks, Jennifer. So is there any question?
Great talk. I think I might have missed it. You said so many interesting things. So Accelerator is working on this 2023 data that was unfiltered. In terms of like moving forward, it's already on trigger, but how is it going to be incorporated with the new data that's coming in?
Right. So okay. So now it's integrated in the production firmware. So it means that it's now together with the other algorithms. So which means we just need now to push a button to say, okay, now take data. And we're going to do it. We're now just monitoring that everything is fine. And once, and I think in the next week, so we start taking data, and they allowed us to get 300 Earths for the whole year. So we're going to have some events at the end of the year.
I see. So some amount of the data coming in, the trigger decisions will be made by the neural network.
Exactly. Yeah.
What percentage of the data is that roughly? Just
that's it's tiny, maybe even, I don't know, 300 Earths, and we're gonna get. Yeah.
3%, 0.3? Okay. Still.
Yeah.
Congratulations. That's really exciting.
Yeah, we're also getting like almost a kilohertz, but in a different. So because we want to use the low rate threshold just to do mostly commissioning, and but we're gonna get like a higher data set, more like of a kilohertz, but in a reduced format. So it's called HLT scouting format, which has let's say coarser or less information than the full than the typical prompt reconstruction. Yeah.
It does interfere. Okay, excellent. First, congratulations to you and CMS on the anomaly detection analysis. I know it's been many years coming. People have been talking about it for a long time, so it's awesome to see it. Also to see a comparison between different methods, because people have been arguing what would be actually better or not. And so the complementarity is really great to see.
Yeah.
So you alluded to a little bit on your kind of challenges slide. You didn't see an excess, but if you had seen an excess, was there a plan within CMS about what you would have done if you had actually seen something? And did that have to be decided ahead of time before you actually did the analysis?
Next question. Well.
The short answer is there was a plan. No. It wasn't that bad. There was basically the plan was, so Jen showed maybe, I don't know if I don't want to answer your question.
No, go.
All right, so Jen showed our correlation plot of signals, right?
I removed it actually because I don't like it. But I can pick it up.
Sorry. Yeah, so all right, she was going to show it when we tried it.
I was afraid it was going to raise a lot of questions. Here.
All right, yeah, I'm
Ah.
willing to to defend these plots.
Okay, defend it.
But basically, this is the actual kind of correlation after some selection on signal hypotheses and background. And the interesting thing is you'll see that some methods which tend to be similar tend to be correlated on the signals. So for example, TNT and koala hunting, which are very similar. And then some methods, a lot of methods tend to not be correlated, which was a big surprise to all of us because we thought we would all hone in on the signals. The other thing to know is that the background is completely uncorrelated, right? Which basically means we're all selecting kind of different events, right? So which says that, one thing you can go from this plot is say we could combine all of these and make a super anomaly detection algorithm. But another thing you could say is that if we do see an anomaly, right? So first of all, right, these are two of the, I think, order 100 signal models we tried, right? You can make this plot for all 100. And if we saw an anomaly, first thing you would do is, depending on which category was sensitive, you could hone in on what that would be. And then you can also take these selections and kind of do observable studies and things like that. And like we had things like this in place, right? It wasn't something we had not thought about per se, but like, we didn't execute it. So it feels.
We didn't test it. We could have tested it.
Yeah,
But we haven't. We could have, inject some real signals and see.
I mean, we found an anomaly in the sideband, right? So we found top quarks, right? I don't know if you were following this,
No,
right?
missed that part.
So yeah, we did find, so in one of the channels, the Quack channel, we found top quark events, right, in the background. Right? We did a test on sidebands where we didn't expect signals. And the sideband region was so kind of calibrated and cut that it generated a peak from top quark backgrounds. We were the only ones sensitive to this. Just by the nature of Quack being very sensitive in certain topologies. And so we saw this excess and kind of explained it and spent like 3 weeks kind of going into detail, explaining all the features. That may or may not get public at some point, but the point being is that, there was kind of schemes where we did unblind and we saw things and we had to sit down and reinterpret. I mean, ultimately in that case, right, we were pretty sure it couldn't be a signal because it was control region where you don't expect signals. But we knew it could have been one of the backgrounds. So we just kind of systematically went through and ultimately made a more kind of directed search. We made because we can kind of change the level of inductive bias with Quack. So we made a new analysis and like the top quarks appeared very quickly. So we knew it was top. But yeah, I mean, these methods work, right? It doesn't, you can't tell from this paper, which is a little frustrating.
Any other question?
Yeah, so thanks for the great talk. I was just curious. So you had this slide where you showed all the different methods from like most model independent to most model dependent, and you showed the features that go into them. And the more model dependent they were, the higher level the features were. And I guess I was just curious, like why that was, what would happen if you tried, high level features on the model independent approaches.
Yeah, that's something we want to try actually. Yeah. So I mean, you can make an autoencoder, yes, with the same features. Yeah. Just that. So I think what we wanted to. So the thing is, we think that these methods should also be used not for this type of jets, which are, I mean, we know them very well. They have substructure and so on. So we know, but we would like, I mean, to probe. I mean, at some point to just, read or let's say add more features that are not related to just substructure, because maybe you want to look for long-lived, long-lived objects or objects with a huge, not normal number of leptons inside. So I mean, you want to expand or extend these methods to different, to new, let's say, I mean, to cover more of the phase space, and eventually maybe use just all the particles in the event without even thinking if there are jets or like what they look like and so on. So I think that's why we wanted to keep the variation autoencoder like this, because then the next iteration is going to be not this type of jets, but something different, something, yeah, more broad.
So does
And-
something, sorry, does something prevent you from doing like quack with constituents?
Yeah, the others, I don't know the scale though. The weakly supervised method, I'm not sure they scale very well with number of inputs.
Sorry, you guys are asking too many fun questions. If you look carefully, you'll notice that there's cathode and cathode B, and I think they remove. So you'll see that the number of inputs there are actually less than Quala, TNT, and Quack. That's actually because if you add, the reason they had separate was that even adding the B made it like things worse, right, in other things.
Yeah, they didn't scale at all with the number of inputs. Instead of variation autoencoders, yes, I can make it a graph. Now, okay, we use a Conv1D, which was not the best architecture. We didn't have time to optimize the architecture. But if you use like more like a graph autoencoder, you can really put more inputs.
Yeah, but the middle approaches don't work very well with large number of inputs, right? There's like 20 papers discussing this. I'm happy to point you to literature.
Yeah, also they have problems with the with correlations with the digit invariant mass with these features. So they had to do, there was a lot of engineering, reweighting, and rechecking. So it's like yeah, or a bit cumbersome. The variation autoencoder is probably like the easiest thing that we could do.
Yeah. If there are no more questions, I see there are 2 messages in the chat, but I don't know. From before. Okay, fine. So I think we can close it here if you don't have any more questions. And let's thanks again